Okay, this is lesson 6.4, quadratic models. So what is a quadratic model? Well, it represents quantities that are non-linear, so not lines. And since it's not a line, it won't have a constant rate of change. So in a table of values, we'd be looking at the second differences. And if the second differences are equal, we have a quadratic model. For graph, we're looking to make sure that that curve is a special type of curve called a parabola. And if we're looking at an equation, it should have a degree of 2. So something that has a degree of 2 will have an x squared term. And it can have any degree under that. It can have an x term, and it can have a constant term as well. But the key is that a can't be 0. It has to have that squared term. So that becomes pretty important when looking at equations. Degree 2 ax squared term has to be there. So first, let's look at tables. We've got first differences. And if we're comparing consecutive y values for our first difference, the first step is down 12. The next step is down 36. And we can get those numbers just by subtracting. And the last step would be down 60. And if we look, the first differences aren't the same, so we don't have a parabola. Or sorry, we don't have a line, so we may have a parabola. And we can check that by looking at the second differences. So what's happening to consecutive first differences? Well, I'm going to do the math on a calculator here. We're going to take the second first difference and subtract the first one. So it would be negative 36 subtract negative 12. And we get negative 24. We're going down 24. And the next one would be negative 60 subtract negative 36, negative 24 again. So now we have constant second differences, and that is your trademark of a quadratic. So because we have constant second difference, therefore it's quadratic. We know that if the first differences are the same, it's a line, and we can stop there. If we find out the first differences are the same, we just say it's a line, it's linear. But if they're not, then we can look at second differences, and if those are the same, we can say that it's quadratic. Let's look at one more table. So if we compare consecutive y values, we'll be looking for first differences. And if we do that, these numbers are going up, first by 16, then by 24, then by 36. And if we compare these, 16 to 24 is up 8, 24 to 36 is up 12. Neither the first differences or the second differences are the same. So this is not a line, nor is it a parabola, nor is it quadratic. So since neither are constant, we can say, well, since the second differences aren't constant, that means the first aren't. We can just say that it's not quadratic. It's also not linear. But we would never look to see if it's quadratic if it was linear. So if we get not quadratic because the second differences are different, that implies it's not a line also. So this is some other type of relationship. On a graph, we're looking for a parabola. So the first graph is a parabola. So we can say it's quadratic. How do we know it's a parabola? Well, parabola will either have a maximum or a minimum. This one has a maximum, and it'll also have an axis of symmetry. So it'll have a line that splits it in half. And if we have that, there's also a step pattern that it should follow, but if you get a curve that looks symmetrical and has a max or a min, for our purposes, it's going to be a parabola. In D, we've got a line, so therefore it's not quadratic. Equations. We have two equations, E and F. If we look at E, E has this x squared term, and if we look at F, we've got a 3x term. We don't have an x squared term. So because we have a squared x, this is called degree 2, and this means it's quadratic. Degree 1 means it's not quadratic. It is in fact a line. So there's how we can tell whether it's a line, or sorry, a parabola or quadratic by looking at a table, a graph, and an equation. So a little bit more about equations. Often formulas representing real-world situations contain 3 variables, the dependent variable and 2 independent variables. For example, the formula for the volume of a cylinder is pi, my pi disappeared, r squared h. Volume depends on 2 things. It depends on radius, that's the r, and it depends on height. Now, if we want to tell whether the relationship between radius and volume is quadratic or not, or if we want to tell if the relationship between height and volume is quadratic or not, what we do is we set one of the independent variables to some known value. Simplify the equation and solve for the unknown, and then you can determine if the relationship is quadratic. So is there a squared on our variable? I'm going to show you an example of this. The formula d equals 1/2 at squared gives the distance traveled by a car as it accelerates from a stop position where d is the distance traveled in meters, a is the acceleration, and t is the time lapsed. What's the relationship between distance and acceleration? Well, we can explore that. If we set time to something constant, we're going to set it to 2. So to do that, what we do is we take our equation, t equals 1/2 at squared, and we plug in t equal to 2. That would give us t equals 1/2 a2 squared. And then we just have to do a little bit of math. 1/2 times a, can't really do anything there, but 2 squared is 4. So we got 1/2 a times 4. Can't do 1/2 of a, but we can do 1/2 of 4. Half of 4 is 2. So we're left with d equals 2a. And now to tell what the relationship is, we just look at the exponent on a. Well, it's degree 1. Therefore, it's a linear relationship. What about d and t? Well, same method. Take the equation. We're going to make a2. So we've got d equals 1/2. We're going to make a2, and then we end with t squared. Half of 2 is 1. So we're just left with t squared. And now we can see our variable t is squared. That's degree 2. So therefore, this relationship is quadratic. All right, the last thing we're going to do is we're going to take a table and we're going to fit it to a quadratic model in Desmos. So I'm going to scroll down here, and then we're going to get Desmos open. So if possible, you could open Desmos on another device or split screen here, and we'll work through it together. So give me a second to get Desmos up. Okay, here we go. We've got Desmos loaded. We're going to take our graph of distance and height. Distance on top is going to be our x, and height on the bottom is going to be our y. And this is the distance and height of a fountain of sparks from a Canadarm rocket following an arc in the air. So how far the spark is away from its launch point and how high in the air it is. And I just forgot to fill in these blanks. This is about using a quadratic model. So instead of linear regression, we're going to use a quadratic regression, which means we're going to fit our data to the shape of a parabola. So as linear regression produces a line of best fit, quadratic regression is going to produce a parabola of best fit. And why would we do this? Well, we would do this to use the model to make predictions about distances and heights of our sparks. So maybe they want to know where they're going to land. Okay, so let's make a table. If you remember from the first video on linear regression, we make a table by plus sign, and we can add a table. And then we got our x1s and y1s. Our x's are going to be our distances, so we're going to do 5, 10, 15, 20, 25, 30. And for our heights, we got 43, 75, 97, 108, 109, and 110. And just like last time, we can't see any of our points, so we're going to zoom out. And there's our points. Now we're going to zoom in a little bit and try to center them on the screen so we can see them. And there we have our points. And if it looks like it's part of a parabola, nice. So using Desmos, what we can do is we can insert a parabola of best fit. And just like line of best fit, we use that equation y equals mx plus b. Very similar for parabola of best fit. We use the ax squared plus bx plus c equation I wrote on the first page. We got ax squared plus bx plus c. The only catch is instead of an equal sign, we have to use that squiggle to designate regression. And then since we're using x1 and y1, wherever we have a y, we write 1, and wherever we have an x, we write 1. And there we have it. This is our Desmos regression equation. So if ever you're running quadratic regression, you're going to use that in Desmos to get your equation. So we're going to type that into Desmos and come up with an equation. So we got y1, and then we need the squiggle, so that's under ABC, squiggle, and then we've got ax1, and we're going to square it, so to square it, and hit this a squared button, and then we're going to press plus bx1 plus c. And there we get our parabola of best fit. Turn that off. And if you look, we got an A, a B, and a C. And the A, the B, and the C fill in the A, B, and C in our equation. So since our A, I'm going to round these, B, and C. A is, I just noticed a mistake in the table. It's actually kind of nice that we can work through this together. If you notice that you make a mistake in your table, we can go back and change it, and we don't have to redo any of our modeling because that is set to change based on our points. So if you notice under the 30, I typed the wrong number. I should have typed 100, I typed 110. So if I go back and fix this and make it 100, all it does is it changes our model, it moves our model. And now look at those dots. Those dots are all actually on the parabola, and if we look, the r squared value is 1, which means this is a perfect fit. So these dots are perfectly quadratic. And now we have new A, B, and C numbers. I'm going to switch it back really quickly so you can see that. Look at the A, B's, and C's. We've got negative 0.17, 8, and 5. And if I fix it, these change. Negative 0.20, 9.5, and 0.7. So if you do make a mistake, you just have to change your table. Everything adjusts, which is kind of nice. So let's fill in these A, B, and C with the correct numbers. We got negative 0.206429. B is 9 point. I'm going to round it to 5. I should have rounded this one too. Let's do that. We'll go 3 decimal places. And 0.7. So if I want to write out the equation, we got y equals a, so negative 0.206 x squared plus 9.5x. Be having trouble here. Plus 0.7. Let's fix that number at the beginning. 0.2. There we have it. There's our equation. B says determine the maximum of the regression curve. What does it represent? Well, the nice thing is now that we have our parabola of best fit, if we click on it, we get this little ghost dot at the top. If we click that ghost dot, that is the maximum. So if we round those, it looks like it's 23 and 110. That's our point. So what's this represent? Well, since we're talking about rockets being shot up into the air and then falling, this is the maximum, because it's the top of the parabola, height. And the maximum height would be the 110, the second number. And it occurs at a distance of 23 meters. And say, for example, we wanted to see where those sparks were going to fall and hit the ground. Well, if they launch from here and they reach their maximum of 23, and we go down, we can click right there, they should hit the ground at about 46 meters if they were to fall all the way to the ground, following that parabolic curve. All right, that's it for lesson 6.4, quadratic models. I'll see you in 6.5 when we look at exponential models. Thanks for watching.